You have multiple quantum devices on the very right side. You have a diverse group of users on the left side. And what you're trying to do is you're trying to realize an application from the very left, from an end user to the actual hardware. But along that path, there are many, many, many computationally challenging tasks to be solved, whether that's simulation, compilation, you name it. Lots of them require software engineering, they require tools, methods to be tackled efficiently and automatically. So that's right where we sit, that's right what we do and what the Munich Quantum Toolkit is for. It's a collection of tools that tries to identify the pain points within the whole flow and provides automated and efficient solutions for those pain points. Whether that's supporting an end user developing their application, whether that's the classical simulation of quantum systems, the compilation of those programs to hardware, the verification of those applications, or error corrections, or the actual design of hardware themselves, all supported by data structures and core methods. That's the whole range of software solutions that we try to offer to aid users in realizing quantum computing and utility for quantum computing. So that's what the next couple minutes will be about, but let's first start slow with classical computing. In classical computing, you have a processor, you feed it a list of instructions, that list of instructions gets processed by the processor, you get your results out, series of zeros and ones. So how does that processor work? It works on binary logic, uses all those gates you're all very, very familiar with, AND gates, OR gates, XOR gates. And from roughly 50 years ago to a couple of years ago, we got quite far in developing these systems. So to put these into numbers, like we went from a couple thousand transistors to billions, we went from frequencies in the kilohertz range to gigahertz frequencies, and from a single core to multi-core systems. And the big question is, how? And one of the answers to that question is design automation. No one is designing these systems by hand anymore. You couldn't. You couldn't draw that if you had endless time. We have tools and software that takes this role, that helps us, that guides us, and that helps us develop efficient solutions. So design automation was the key for classical. Now let's look at how this looks in quantum computing. Actually not that different. Instead of the classical processor, you have a quantum processor, and instead of the assembly program on the left, yeah, you have a quantum assembly program. Still just a list of instructions. The output actually is the same. Still get a series of zeros and ones out of there. Internally, of course, it works a bit different, and I'm not going to lecture you on quantum computing now. You're all familiar with how it works. You have a state represented by a vector of amplitudes, you have matrices or operations that are represented by matrices, and applying an operation to that state gives you a new state. And if you want to do a quantum computation, you just zoom out a little bit, you start with some initial state, you plug that into your computation, for every operation you apply it, you get a final state out of there, and then you can measure that state and get out your classical result. You repeat that process over and over again. That's how you do quantum computation. It's not that difficult actually. But where's the catch here? And you all know the catch. Like the catch really is, for n qubits, these vectors and matrices are exponentially large. So it's really hard to deal with those on a classical computer. And just to put this in a little bit more perspective of how quickly this complexity grows, let's look at the state vector sizes. For 2 qubits, it's 4 amplitudes. You can probably do that by hand or in your head. You can just compute that, pencil and paper. 12 qubits, just 10 qubits more, takes 64 kilobytes of memory, fits in the fastest CPU cache, so not that big of a deal. 10 qubits more, still in CPU cache land. 32 qubits takes already 64 gigabytes, so that's probably what your laptops that you're all using, they're at capacity with that qubit size, if you just represent that vector. If you take 10 more, it requires a supercomputer, and even that might struggle. And at 305, you have more amplitudes than atoms in the universe. So we saw just earlier in Leon's presentation, IBM's latest device, 433 qubits, so even more than atoms in the universe. How are we going to deal with that complexity that's ramping up so quickly? And how? Like, our answer is again design automation. Like, let's repeat the success that we had for classical systems, for design of classical systems, also for quantum computing. Many of the problems are indeed similar. They have a slight quantum twist, but we can use the knowledge we gained over the last 50 years in design automation for classical systems also for quantum systems. And that's what we do as a chair, as a research institution. We develop tools for exactly that. And how many of you in here have heard about decision diagrams before? Well, that's actually quite some. Also for quantum computing or just binary decision diagrams? Who has heard of quantum decision diagrams? That's fewer. So they don't look like this. This is generated by some deep learning. But I think it's still quite fitting. So I'm not going to give you an introduction about decision diagrams as a whole. Check out the paper there. In a way, they are data structure to represent quantum states, operations, to do manipulations of those states, and to sample from states. And they're a sparse, reduced, and normalized data structure. If you want to know more about them, please approach me afterwards. I'm happy to talk about it for hours, but that's not the place here. That's for outside. So I want to keep this a little more hands-on. How you can represent states, matrices, you can do matrix vector multiplication, and you can sample. So what you can do with this is you can perform classical simulation. And how does that look like? We really believe in the educational character of things. Like, we'd like to educate people on how this data structure works, how quantum computing works, how algorithms are simulated, how the state evolves. And we developed a tool for that. It's called DDVIS, and you're happy to follow along if you have a laptop out anyway. So either go to that link down below or scan the QR code. If everyone does that, probably the site crashes, so maybe not everyone should try, but if you want to or try later on, please do so. What you see here is on the very left side. Let me see if that works. On the very left side, you see an algorithm description of Grover's algorithm. It's a simple 4-qubit example, very simple oracle, but yeah, it is what it is. In the middle, you see the decision diagram representation of the current state, and on the right, you see the state vector that this decision diagram is representing. It's in the all-zero state at the very beginning, and then in this tool, you click at this advance button, then you apply the state preparation of Grover's algorithm, which you're all familiar with probably. The flag qubit on the very top is in the one state, and all of the other qubits are in an equal superposition. This is very nicely reflected in that data structure. If we now apply one of the Grover iterations, which is the main component of the algorithm, by clicking this button again, then we get the following. And from the state vector, you see the typical Grover effect. You see this amplitude amplification of the desired state. And that actually is pretty nicely reflected in the decision diagram as well. The top qubit is still 1, but over here, you really see this qubit has a high probability of being 1, here again, and here again. If we apply one more step, so the final step of Grover, then this amplitude gets amplified even more. That's just how Grover works. The structure of the decision diagram didn't change, the edge weights did, and they reflect again that the probability of getting the right state is even higher now. So that's an app, that's a tool, software we developed for you to explore this data structure that's certainly different than what many of you might be used to. Like, you might be used to tensor network methods or something like that. This is an alternative that's definitely worth checking out and that yielded promising results. But of course, those promising results are not based on a web GUI. They're based on a proper tool that's implemented in a performant fashion. And that's our MQTT-DSIM tool. And what we believe is that a complicated tool doesn't need to be that complicated to use. So we really value tools that are accessible to users. And our tool is just a single pip install command away. So you install your package, then you design your program. For example, let's say you write a Qiskit circuit, just a very simple one. So just bear with me, it's a simple one. It works for more complex ones. You print that circuit by executing that Python script. Just looks like this. You all know that circuit. And then the code that you need to use our simulator is just the typical Qiskit code you would write. You get a provider from our package, you execute that job, you want 100,000 shots, pretty easy to do for our tool, you get the results, you print them, and what you get is the expected result. It's as easy to switch from your typical workflow of maybe using Qiskit to using our simulator and trying out decision diagrams for your use case. And just as a small advertisement, Qiskit primitive support is coming soon for that, so you can also use your sampler, estimator, whatever you want with our tools. So I just want to throw some buzzwords out there to trigger some discussion later on. Like, what did we do with classical simulations using decision diagrams? What can you do with that data structure? For one, you can do strong and weak simulation. So you can emulate a quantum computer, you can get the full state vector. You can also do approximation techniques. You can cut off things. Let's say you're fine with 90% fidelity, then you can make your decision diagram smaller, make the simulation more performant. You can simulate dynamic circuits, a quite timely topic we heard about in the talk previously. You can do that out of the box. You can also explore something similar to circuit cutting, actually, which was also covered in the previous talk, but for classical simulation. Like it's another example of a technique that's used for making something run on a quantum computer, but that can actually also be used for classical simulation to make it faster, more scalable, more parallelizable. So that's out there. You can, of course, also do noise-aware simulation because density matrices are also just matrices, so why not represent them as decision diagrams? And we started to explore Hamiltonian simulation and estimating some observables of systems and how decision diagrams can help here. If any of those trigger your pain points in the flow, please find me later on or someone of our team. We're happy to talk about it. But so far about simulation. Let's take it even one step back, and let me go one step back even more. Let me get a quick show of hands. Who of you is still writing assembly on a daily basis? Yeah, I expected that. What people frequently do is they write something in a high-level language, like C++, Python, and they use a compiler to compile their things down to something the processor can understand. How does that look in quantum computing? It's not too different, actually. You also write your stuff in Qiskit, Cirq, whatever high-level SDK, hopefully in the future even higher level, but still, you write it in a high-level language, you compile it to some instruction set, then you run it on the computer. So let me just quickly walk through the steps that are necessary to run a conceptual algorithm, again a Grover example here, on a quantum device as sketched there. First of all, they all have a limited gate set. There are no arbitrary gates allowed there. For example, most of them don't support 3-qubit gates. So you better decompose that in a process called synthesis. This makes the circuit larger, but okay, at least it only contains gate that can be executed. In addition, many architectures have a limited connectivity. So you also need to account for this in a step called mapping. That's typically split into many different things, like finding an initial layout, assigning the circuit qubits to the device qubits, then executing as many gates as possible, potentially inserting some swap gates to make the connectivity fit, then executing the rest of the circuit. That would make the circuit executable, but that circuit is pretty large. So what you do, due to limited fidelity and coherence, is you apply optimizations to get the size of the circuit back down to something that's hopefully also performant. It's a very, very, very limited view of how you could view compilation, but in the very end, it addresses two hard challenges. Synthesis and mapping address the limited connectivity and the limited gate set, and then you do a lot of optimization. And I'm going to come back to one of Leon's points that it's not a sequential flow. Like, it shouldn't be. So on the pipeline discussion, I'm probably with you. But let's come to that in a second. I'll quickly want to highlight where design automation can help here, focusing on the mapping problem. Like, the mapping problem is you take a decomposed circuit and you want to map it to the limited connectivity of a device. And you can do this in various different fashions. And all of them kind of offer a trade-off between runtime and the quality of your result. You can either do this very naively, this is fast, but the quality will be poor. You will be inserting many swap gates, and yeah, expect nothing good of that circuit. You can do this heuristically by doing some clever tricks, optimizing the number of swaps. Probably it's the middle ground between runtime and quality. And you can do this optimally. So really looking for the least number of swaps possible. But as it turns out, finding the optimal solution is an NP-complete problem. So it's really, really challenging to arrive at that right circuit. And it will cost you a lot of runtime to determine that. And it probably isn't that scalable for large-scale systems. But this is kind of the problem that frequently arises in classical computing as well. All these placement and route problems, all the expertise over the last 50 years on these kind of problems can help here. So what we did is we developed a solution based on the symbolic encoding of that problem. Don't question the details here. Like, if you're interested in that, please see me later on. But what this more or less is these are just constraints that encode what is a valid mapping, in addition to a cost function down below that tells you how costly that mapping is. And you can pass that to a satisfiability solver, and it gives you back a solution that's guaranteed to be minimal in the number of swaps. So again, it's using the classical expertise we developed over decades for a new kind of problem that's relevant for quantum computing. You might wonder again, how easy is it to use that? And the answer, again, is pretty simple. It's a pip install command away. You just import Qiskit, import your circuit, import our tool. The circuit looks like this, it's the circuit from the previous slide. And then it's a simple QMap compile. You pop in your favorite architecture here, you use the exact optimal method, you print the resulting circuit, and you get that circuit with a one single swap. If you want to check that out, that's the QR code for you. The link is above. Feel free to do so. It should be easy to use, it should be easy to install. It works hopefully everywhere. Again, some discussion points, some points where discussion could arise outside or maybe later on. We looked at optimal and heuristic mapping techniques for superconducting computers. We also looked at the synthesis and optimization of Clifford circuits. Tom in the first row here is probably the person to talk to in that regard. So feel free to approach Tom. We also considered the compilation for multi-level systems. So what if you don't have qubits, but qdits? Kevin in the very back there is your person to go to if you want to talk about that. And we also talked a lot about like the higher level part of the compilation toolchain. Reversible, oracle synthesis. How can you get a reversible specification of some classical function that you want to use in Grover's algorithm, for example? We need higher level languages to support those. No one is going to write individual instructions anymore in the future, hopefully. So, back to compilation we go. That's the toolchain we have right now. Who actually tells us that what comes out of that compiler still does realize the same functionality we originally intended? How do you actually verify that? And you might ask, is this even an important question? And the recent study shows about bugs in quantum computing platforms that, yes, this is an important question because roughly 40% of bugs are quantum specific, and they mainly occur in components that represent, compile, and optimize quantum programming abstractions. So in this process, compilation, many bugs can arise, and we need to have methods that make sure that everything is still correct. So how would we go about this? How would we do this? Let's say we have two circuits, a realization, or a conceptual algorithm on the left, and a realization on the right. In principle, the question is easy, because as you know, every gate is a unitary matrix. We multiply them up, get a big matrix U, do the same for the second circuit, multiply them up, and we just compare those matrices, right? Yeah, same catch as for simulation. Those matrices are exponentially large, so not a scalable approach at all. What can we do? First try, similar to the classical realm, what do people do? They have two classical circuits, they build decision diagrams out of both, and if both represent the same functionality, those decision diagrams actually coincide, and that's it. So, you would just compare the root pointers of those decision diagrams and conclude, yeah, these two, they are equivalent. But you would construct potentially two very large decision diagrams. So this is a data structure that's still exponential in the worst case. It can be quite compact, but in the worst case, yeah, tough luck. We can do better than that, actually. So under the assumption that two circuits are equivalent, I hope you all agree with me that if I invert one of them and match that together with the second circuit, that should realize the identity. So the inverse is easy in quantum computing, something very unique that we don't have in classical. Classical, not everything is reversible. Even a simple AND is not reversible. But in quantum computing, we just flip the order of gates, invert every gate. That's it. So going left to right, this should realize the identity, right? Yeah, it's a good idea. We would still construct a complete decision diagram for one of the circuits. So yeah, not quite there yet. But what do we do the following? We start with the identity in the middle, decision diagram representing the identity in the middle. Then we apply a gate from the right side and one from the left side. We're back at the identity again. Let's do it again. One from the right side, one from the left side. One from the right side, and a couple of gates from the left side. And I hope you get the idea by now. One from the right side, one from the left side. One from the right, one from the left. The overall idea here is that You start in the middle of both circuits with the identity, and you alternate between applications of both circuits with the goal of staying as close as possible to the identity during the verification process. And of course, the natural question is, how would you do that? How can you derive strategies for when to go left, when to go right? The answer is, you can actually exploit knowledge about the compilation flow. These two circuits aren't completely unrelated in most cases. If the one is the result of compilation, then you know roughly what the compiler was doing. So you can use that as a basis to derive an efficient verification strategy that allows you to verify compilation results on the large scale, because you can always keep close to the identity. But quantum computing has even more to offer, and I'll keep talking about verification a little more because it's a very timely topic and it's very important, and there are certain opportunities that we don't have in classical computing, like this reversibility. It's not for granted. So let me show you what else you can do. You can, for example, take both circuits, you shuffle a computational basis state, you put it into both circuits, simulate those circuits, get the output state, and compare those output states, compute the fidelity or some similarity metric of those states. And if that's close to 1, yeah, then you continue going, you shuffle a new random state. If not, you found a counterexample and those circuits are not equivalent. Yeah, you can do the same in classical computing. It's not going to work out well because of masking effects and everything. Like, you won't identify errors just by random sampling. So the big question is, how likely is that negative outcome? If my circuits are not equivalent, how likely is simulation going to be to detect it? The positive answer is that this reversibility of quantum computations makes it way, way easier to detect changes, and even the slightest changes in circuits frequently affect the entire functionality, meaning that if you just do a couple of random simulations and they all turn out positive, then you can pretty much be sure that you're good. And if not, then one of those random simulations will most likely yield that negative result. At the chair for design automation, we like to put all of this into a big picture. Like, we have two approaches, but they work well in tandem. You start first by doing some simulations. If one of them turns out to reveal the non-equivalence, then all good. If not, then we keep a list of things, and we go again if we're not completed. If we have performed, let's say, 10 simulations, we go on and apply the second verification scheme, where we just do this left-right thing, and either that turns out to yield the non-equivalence, the equivalence, or it could very well happen, because this is a challenging problem. The equivalence checking problem is actually QMA complete, so it's even tough on a quantum computer. It could very well be that that method times out. And in that case, due to these reversibility effects and these errors not being masked that much, that still, the simulations you did prior to that still give you a very, very, very high confidence that your circuits are equivalent. So compared to the classical case where you almost know nothing if you just did 10 simulations with random inputs, you really know quite something. Again, this looks all quite complicated, but it's still easy to use, and it should be. Like, we really believe that just complex tools shouldn't be complex to use. Again, pip install command away, you define your circuit, as simple as that, you're used to that, you compile your circuit using Qiskit, for example. There's no real resemblance anymore between that circuit and that circuit. At least it's not that apparent. And the single call that's required to verify those circuits is a single QC verify compilation and yields equivalent. That's it. I think this is quite a unique opportunity. One couldn't appreciate more, because right now is the time to avoid a situation where we have powerful quantum computers, but simply no means to design for them or to verify any applications for them. We're in a dire situation in the classical world where we can design the most complex circuits, but we have no chance of verifying them anymore, leading to various problems all around. Now is the time to change that in quantum and to not repeat that future. So, again, some pain points on verification. Like, it's all about verifying the result of compilation flows, but it's not about that, and it's for sure not only about decision diagrams, if you're wondering. We're also doing ZX-based equivalence checking, and here Tom again is your man to talk to. It's a pretty neat approach that's also complementary to both existing techniques shown earlier. We can also verify dynamic quantum circuits, because as they arise as a practical feature, of course the question arises, how do you verify those? they are not unitary anymore. A measurement is nothing unitary, a reset is nothing unitary. How do you handle this in verification? We have thought about that already. And also very timely, the verification of parameterized quantum circuits. All applications that we're currently exploring, most of them, somehow have to deal with variational quantum algorithms. They all have symbolic parameters. We also need to think about how to verify those. All right. Going back to this overall picture once more. I'll probably go back to it a couple more times, but let's see. What we've heard so far, I'd like to do a quick recap, is we have our core tools, core methods and data structures that support this whole flow. Decision diagrams, ZX, and intermediate representation. We've heard about DD-SIM, that's used for classical simulation of quantum circuits, about QMAP, that helps in compilation of quantum circuits, and about QCEC, that helps in the verification of quantum circuits. But that picture is not yet really complete. Like this, let's focus on that part a little bit. That compiler error looks so small, when in reality, it's a lot of decisions for a user to make. You have to choose one of the many available devices where the number of devices is growing by the day. And compilation is not just a sequential process, left to right. You have back edges, you have loops, you undo things, you optimize again, suddenly your gate set is messed up. So there are multiple sequences that you can take, actually infinitely many sequences you can take through this diagram right here to compile your circuit. There are multiple SDKs, multiple techniques, multiple research proposals. An end user is simply overwhelmed with all of this. Which options to choose, how to compile, which device is best for the application. So we need to think about this, and this goes in the direction of prediction that Leon was also mentioning. So what we came up with is the MQT predictor framework, and I'm just going to sketch this briefly, because what we did is we first threw all those different compilation passes into a reinforcement learning toolbox. Just make everything possible, everything as a single pass, you give it a circuit, and it is allowed to apply any potential optimization pass. Then it learns for a specific circuit, architecture, and a figure of merit, optimization criterion, like the expected fidelity, how to best compile your circuit. And on top of that, we build a machine learning model that then tells you which device you should prefer for a certain application. Like, you have a VQA for an optimization problem, it tells you prefer that device, and it gives you an optimized compiler for that device. So it really automates all of this decision-making process, and I'm actually pretty happy to announce this. The new version that does all this has released just yesterday, so many thanks to Niels. He's back there. That end, talk to him when you're interested in these kind of topics. Very excited about it because it aids end users, it takes away this realm of decisions and gives them clear guidance on how to proceed. So, instead of the compilation error, put the MQT predictor in there. Let me zoom out one more time here, because in the very end, that's only two steps. That's only the compilation and the execution. In reality, when you want to realize quantum computing applications, you have a certain classical problem, then you need to select the quantum algorithm, you need to encode your problem based on that quantum algorithm, and then at the very end, you have to decode your problem. And right now, this is all done manually. Like a domain expert on the very left has to know everything. He or she almost has to be a quantum physicist, an expert, to understand all of that. We really believe that in the future, this should all be abstracted away, and quantum computing it should just be an accelerator, like a GPU, like we take it for granted. It takes the same classical inputs, it produces the same classical output, and we have an envisioned framework for that, which we call the MQT problem solver, that kind of tries to shield end users from all those intricacies of quantum computing and more or less guides them by providing an algorithm selection for their problems to solve, taking over all this encoding, execution, decoding, and then handing them their solution back. So make sure to check it out. Heads up, it's still very preliminary, but it's our vision to make that even bigger and greater in the future. So, back to that overall picture. we're still missing, if you remember the intro slide, it's been a couple minutes back, but we're still missing like 2 points that are on the very right side. So we just took a zoom out, so to say, to the application domain. We should probably also look at the hardware itself. And in that regard, error correction and hardware development are also becoming more and more important, which is why we are also exploring that. It's very initial contributions, but I'd still like to highlight them because we believe they are important. One of them, for example, is a real implementation of a decoder for QLDPC codes and the scalable heuristic that makes this a little more performant, which we identified as a pain point from stakeholders. Second contribution was about decoding quantum color codes with Maxat, which is actually kind of a funny story. I think I have the time to tell that story. Yeah, I'll take the couple minutes. Because this contribution originated from a tweet by Craig Gidney that just said, hey, we have this important problem in error correction that can be mapped to the so-called lights out puzzle. I don't know how many of you know that classical puzzle. It's about lights and switches, and you press switches to turn off lights. And the question is, can you press the switches in a certain order to turn off all the lights? That analogy was more or less all we needed at our chair to develop a solution for that is state-of-the-art worthy and achieve state-of-the-art results. We need this kind of method because we are no quantum error correcting experts yet. We try to become, but not yet. But we need this kind of models of problems that are important to solve, and then we can work with that. Another example is the automatic implementation and evaluation of error correcting codes. So many people are thinking about code constructions and how to best deal with that, prove theoretical properties. But when it comes to practice, there are not that many tools out there that you can actually press a button on and you get an error corrected circuit of something. We tried to do that in one of our works. And last but not least, I'd also like to highlight one of our initial works towards designing quantum computing architectures. Like, we always adjust our circuits depending on the architecture we have. What if we turned this picture around a little bit and designed our architectures based on the applications we have? That's more or less what's going on there. Jack is somewhere in the audience. He's the one to point back over there. All right, that's more or less what all this was about. The Munich Quantum Toolkit is really a collection of tools that helps in the development from application support or classical simulation, compilation, verification, error correction, and also hardware. So it really tries to support people from the end user domain to the physical experts and anywhere in between. All of that is actually open source available. This is a collection of tools that we developed over the last couple of years. They're all open source. We really value that. We see a lot of value in making this kind of contribution to the community, giving back, so to say, letting everyone build on top of that. And also the call, get involved and please contribute to this. We'd really appreciate any kind of contribution towards our toolkit. And yeah, that's the Munich Quantum Toolkit for you. Thank you. Just a very small thing to add. You all fancy merch and stuff like that. If you want to get a sticker for the Munich Quantum Toolkit, please approach me afterwards.
Thank you, Lukas. Are there any questions? Austin again.
Could you say a little bit more about your quantum error correction efforts? It's great to see you working on that.
Let me just get back to that slide a little bit. Then I'm sure I can do it. So, as said, this was really meant as a teaser because we're really just trying to explore what are the pain points in quantum error correction where our expertise can help. And I'm sure decoding is one of those problems where the expertise of the last 50 years in design automation can certainly help because it's a tough problem, it's challenging. We have the tools and methods to apply to these problems. Like Maxat is a great example. We're also trying to find some heuristics to make it a little more scalable. I also believe this top right direction of automatically applying error correcting codes to certain algorithms, to certain problems, also more or less going in the direction of maybe resource estimation, like how many resources do you actually need to realize a fault-tolerant version of your algorithm. This is something that we have on the horizon. If you have further problems that are of interest to you, where you feel like you could use our expertise, then let's talk.